Welcome, everybody. Can you hear me in the back? Great. So? Yeah, no? Great. Welcome to Imperial College. I'm Simone Buitendijk. I'm Vice Provost here at the college. And it's a real honor for me to have Professor Carl Wyman here, who's going to talk about taking a scientific approach to science and engineering education. And all of you who are here must be aware of his fame and notoriety and his status as a world-leading educator, especially in higher education. So we're absolutely thrilled that he's here today. There are quite a few people in this audience from outside of Imperial, so welcome especially to you also. But I also know that there are loads of Imperial staff who do a lot of teaching and support staff who want to learn about new ways of engaging our students and new ways of teaching them. So after my short introduction, I'll ask Professor Wyman to come up and give his speech, and he will talk probably for about 45 minutes or thereabouts, and then there will be about half an hour for questions and answers, because no doubt you'll have a lot of questions that you want to ask him. After that, there will be drinks just outside this lecture theater for about half an hour. And then I'm sure most of you will have other things to do tonight. So again, it's wonderful to have you here, Carl, and we're really honored that you came all the way from Stanford to be at Imperial today. Just to give you a little bit of background on Professor Wyman, he earned his Bachelor of Science in 1973 from MIT and a PhD from Stanford University. But he's most well known to most of us for the fact that in 2001 he won the Nobel Prize in Physics along with two colleagues for fundamental studies of the Bose-Einstein condensate. But he's also been very active in higher education even before he won the Nobel Prize, and that shows from his CV. He was in 2004 named United States Professor of the Year among all doctoral and research universities, and I know he's actually really proud of that. He joined the University of British Columbia in 2007 and headed the Science Education Initiative there, but he kept an appointment at the University of Colorado in Boulder, where he headed a very similar science education project that he founded there. In 2007, he was awarded the Oersted Medal by the American Association of Physics Teachers for his contribution in teaching in physics. And he was also the White House's Office of Science and Technology Policy Associate Director of Science from 2010 to 2012, with that president that we all like a lot more than... I don't have to say more, do I? He joined Stanford University in 2013 with a joint appointment in the physics department and the Graduate School of Education. Again, the combination of research and education. And I think Professor Wyman is living proof of the fact that excellence in teaching and excellence in research can very well coexist. And there actually is evidence, real research evidence that shows that. This is anecdotal, but I think it's really great proof for today. There is research evidence that there's not an inverse correlation between being really good in teaching and being really good in research. So why is it so timely that Professor Wyman is here today? I think we're all aware that we're experiencing quite extraordinary times in higher education. To put it mildly, maybe sort of in a British way, there's diminishing acknowledgement of the value of research and science in many places on the planet, and diminishing funding for universities, and of course that worries us all a lot. At the same time, some governments, especially in Europe and also in the UK, are paying more and more attention to education and the quality of education at universities. And I think that would be really good news if it weren't for the fact that it's very hard to measure education quality, especially at research-intensive universities such as Imperial. So they're not easy times for universities. But I think the only way to actually get out of this and to keep leading is to keep focusing on our core missions, to keep doing excellent research and to keep producing research results, because we all know that none of the global challenges can actually be solved without universities globally working together multinationally and multidisciplinarily. But maybe even more importantly, we should be very keenly aware of the fact that we're training the next generation of global leaders, and we're training them to think critically, to use scientific evidence in their decision making, and to hopefully do a better job for their children and grandchildren than our present generation seems to be doing for them. And that means we need to train huge groups of bright young people. And I think that actually is one of the most important, if not the most important, missions of research-intensive universities. And we want to teach them well. We want to teach them in a way that they actually have the attributes that they need when they graduate, the attributes to solve problems, to work in groups, that we don't just focus on knowledge, which is very fleeting and quickly obsolete and can be found pretty much at anybody's fingertips nowadays with the internet, and many questions can be Googled for their answers. So we really need to teach our students something different than mainly facts. And most of all, we need to see them, take them seriously, work with them as partners, and also attract students that have less opportunity from their cultural or social or ethnic background to get a really stellar education, and make sure that they come to universities such as Imperial and they thrive and they can actually be at their level of excellence with lots of other students. And that way I think we can do a really great job for the world. But that means we have to teach evidence-based, and we have to apply the same rigor to our teaching as we're used to applying to our research. And Imperial has written a comprehensive learning and teaching strategy in which we use a lot of this thinking and actually also use a lot of Professor Wyman's insights and knowledge. And there will be a significant amount of effort and energy and also funding that we're going to be spending on this strategy for probably the next 5 to 10 years, because with any strategy that's really comprehensive and quite big, it also requires a culture change, and that takes time. So we'll focus on 4 areas in our strategy. One is curriculum review, to make sure that students have the space to look beyond the facts and the figures, and that teachers have the space to innovate, and the curriculum is not just full with teaching and assessments in a way that we can't really think beyond that anymore. So that's the first pillar. There's this funny ticking sound. I don't think it's me. No one seems to be ticking. I'll just keep talking. And then the second pillar is a transformation in our pedagogy, and that's basically what Carl Wyman's going to be talking about today, so I'm not going to say too much more about that. The third pillar is creating an inclusive and diverse community, with the emphasis on community, a community of students and teachers, a community of students amongst themselves where they can really thrive and be recognized and feel part of a very exciting academic environment. And that will help them actually achieve. And the fourth pillar is to use online and digital technology to basically support the first 3 goals. And that means we'll have to focus on teaching, and that's going to be a change in our culture where we value teaching just as much as we value our research. So this coming Friday, actually, our learning and teaching strategy will be available on the web for people at Imperial. And pretty soon thereafter, we'll have a shortened version, more like a brochure with the highlights that we'll also share with the rest of the world. And I'm proud to say that we will be the first university that will apply these principles, that will transform the pedagogy university-wide, and that will also immediately combine the online technology and digital technology with our bigger learning and teaching strategic aims. And that's exciting, but it's also a bit scary. It feels a little groundless. We'll really be going into a space that we haven't been in before. So I think all of us are excited, but also a bit anxious. And we need to change our ways of teaching that are so familiar, that we all were exposed to as students and that we've been using for so many years while we were teaching. But I'm very, very confident we can do it for 3 reasons. One is there's already so much innovation going on at the college. There's so many people who are already doing this, but they haven't been brought together so far, and they're too isolated, so they can't share their innovation and their excitement. But we know it can be done because it is being done. And the second one is we don't have to do it alone. If we truly form a community where the teachers also learn and where the students can also be teachers, we'll be in it together. And it really is okay to make mistakes and learn from those mistakes and then move forward as a group. And then we can feel safe, I think, in this big change. And the third one is we really will be standing on the shoulders of giants. People before us have done this, particularly in Colorado and at UBC, so we're drawing from a lot of experience that has already been gathered in other places, and we'll move it forward and we'll make it our own, but we don't have to start from scratch. So I feel incredibly fortunate that we have the work of Carl Wyman to build on, and he's been amazingly generous with his knowledge, also with sharing with us what has gone wrong in his experience in the last 10 years. And that is maybe even more valuable than sharing what can go right. And it's actually more difficult to do that. So I feel incredibly grateful. And he's been tireless in spreading the word and helping so many of us change our teaching in ways that will actually really benefit generations of new global leaders. So I'd like to ask you to come forward, Carl, and tell us about your methods and share with us all your wisdom. Thank you.
Okay, well, thank you. It's a pleasure to be here at Imperial, particularly at a time when they're launching into this great effort to really incorporate many of the ideas that I'm going to talk about today into teaching and improving student learning and success in a way that I think will make it really a leader in the world in higher education. So I'm going to tell you about basically taking a scientific approach to teaching science and engineering. And although I really won't spend time to go into the arguments for it, actually, I hope I'll convince you a little bit that it's grounded in some basic enough principles about learning and expertise that it very likely applies to just about every subject. But before I get into that, I want to give you a little perspective of how I got into this myself and into this way of thinking about it. When I first was called upon to teach, it was introductory physics, so 40 or so years ago, I thought about responded to the same way that everybody, I think, just intuitively when you're asked to teach something. I'd go off and I'd think about the subject really carefully in my own mind to get it all worked out, and so that I could then go tell the students that, and so they could think about it the same way I did. Now, that was the theory anyway, but whatever I've been as a teacher, I've been a hardcore believer in experimental method. And so I would collect data. I would probe the students in some detail. And what I found out is that my brilliantly clear explanations were actually leaving most of the students just quite baffled. And I sampled some of my colleague students, and they really weren't doing any better. And so for many years, I thought this was just kind of like the weather. You might not like it, but there really wasn't anything you could do about it. That's just the way nature was. But I came to see this differently about 30 years ago, not actually because of my classroom teaching, but from working with my graduate students. I had a big atomic physics program, blasting atoms with lasers, working with lots of graduate students. And I looked a lot at how they developed into being physicists. And I saw something that struck me as a very puzzling phenomenon, which is that they would come to work in my research group after many years of great success in courses and exams in math and science. But I'd find they really couldn't do physics at all, at least when they started out, in spite of this great background. But that after just a few years, they had turned into physicists. And so, at first this was just a funny thing about individuals, but after a number of years, I realized, no, there's something fundamental here. This is such a consistent pattern, And there was a particularly striking feature, which was the students who did the best in all their courses and in their exams, they never turned out to be the best physicists. The best physicists were always not that high level in their coursework. And so I got to the point of saying, no, there's a real fundamental puzzle here. I need to figure this out. And I tackled it just like I would a physics problem. I went and dug into the research on how people learned, particularly how they learn physics. I discovered there were a number of people who have been studying that phenomena. And as a result of looking at all that research, I basically found the explanation to this puzzle. It actually made complete sense. And it gave me a completely different way of thinking about teaching and learning, and which I'm going to be telling you about today. Hopefully, it won't take the 5 or 6 years it took me to get this understood. But it also actually got me started doing research on physics and then more broadly science education. And because I discovered, that this was so great from a physics point of view. You could do controlled experiments. You could actually see which methods of teaching actually achieve more or less learning. And so it was much more like a physics problem. And instead of before then, I just, I knew that we had all these ways of teaching that are long tradition or superstition and, no shortage of opinions, but no ways to sort it out. Suddenly this said, no, you could actually measure things and find out what's actually true and what's just erroneous opinions. So that's what I'm going to tell you about, but first I'm going to give you an example of the kind of results that come from taking this research-based approach to science education, particularly at the university level. And so this is one experiment I'm involved with, looking at the learning that takes place in a physics class. We had a large introductory physics class at University of British Columbia, and so we had 2 large sections of this course that we measured very carefully to see they were very, the student population was virtually identical. And we basically taught the 2 sections in 2 different ways and then gave them a test right at the end of that to see which section had learned the most. And the comparison was between someone who was a very experienced teacher of this with good student ratings compared to someone who was a relatively new PhD, but had been trained in these methods of research-based or scientific teaching that I'm going to tell you about. So how did the 2 sections compare on this exam? Well, here are the results, and the histogram, number of students versus their score, and in red is the distribution of students taught with the experienced traditional lecture, and in white is the scientific teaching. And so you don't have to do very complicated statistics to look at that and say, gee, there's a big difference there. And in particular, you should be wondering, here's somebody who by the traditional standards is a very good teacher, and yet their students are learning much, much less than this relatively inexperienced teacher. And so hopefully you want to know why that can possibly be the case. And in fact, the reasons behind that, and I'll go into details, but they really can be understood in terms of results that have come from 3 different areas of research in the last couple of decades that are giving us new insights on teaching and learning. And all 3 areas are giving us now a very consistent, coherent picture of what's needed to have people learn, complex thinking like a physicist, okay? So part of this, one area is cognitive psychologists who study mostly in labs how people think and learn at the basic level. There's brain research that's now tying into that. And then there's the research actually from the university science and engineering classrooms. Engineering doesn't fit there, but we've got data from all of those. And those basically give you the background of how these more effective teaching methods have developed and why they work. And so in the rest of my talk, I'll go into detail on that, starting with the idea of what really makes up expert thinking, thinking like a scientist or an engineer. And I want to emphasize that when I talk about thinking like an expert, I don't mean that you're turning all the students into scientists. I think for the vast majority of students, they might take 1 or 2 science courses, and but they'll go on into other careers and so on. But you still, the important thing you want to have them take away from those courses, and the real ultimate educational goal, is to have them learn to make better decisions in relevant areas, where that means, being able to understand, to take the way scientists in an area think, the knowledge they have, the way they use that knowledge to arrive at conclusions, and have those students be able to use that to make better decisions in their life, in their choice of public policy, et cetera. And so, really, Simone's introduction was stressing quite independently, we didn't coordinate, was really stressing this, that it's really not about remembering a bunch of facts and little bits of information that are really good only for doing well on exams. It's really about having a different, better way to think that they can apply more generally. So first I'm going to go into more detail what we really mean by scientific thinking or engineering thinking, and then talk about how it's learned, and that's sort of the cognitive psychology part. And then I'll give you examples of how you apply these concepts or principles in actual classroom teaching and what kind of results we measure when that's done. And then finally, I'll spend a little bit of time talking about institutional change, how we move teaching from its, universities' thousand-year-old traditions to try and incorporate modern research findings. So, starting with expert thinking, cognitive psychologists have studied how experts think across a large variety of different fields, chess players, historians, scientists, musicians, etc. And they find what to me is a very striking result, which is that there's a very strong similarity at the basic level of expert thinking across all these different fields. And there's also a great deal of similarity of how that expert thinking or expertise is actually developed. So if you look at what the basic components of expertise are, is first, experts in every field have a lot of factual knowledge about their subject. That one would be obvious to everyone, but the others aren't nearly so obvious. It turns out that in every given field of expertise, experts also have, for that field, a very well-defined organizational structure for how all that information is organized, and that it's a structure that allows them to be very efficient and effective at actually selecting and applying the relevant information to solve problems. And these organizational structures involve a bunch of different things, but one simple example is in every area of science where we have a scientific concept. That's actually the way scientists in that field took up lots of different experimental results and different pieces of information and saw a way to organize it all together as sort of a coherent piece that when faced with a new problem, they can very quickly decide, oh, all that information is going to be useful, I should apply that concept, or no, that's not applicable here, so I don't need to worry about it. And so this kind of structured organization just makes one be able to use information much more effectively. The third general area of expertise is experts in any subject can actually monitor their own thinking. So as they're solving a problem, they can be sort of asking themselves and answering, do I really understand this? Is this a sensible way to be solving this problem? And basically answer so that they can say, decide, okay, this is a productive way to be going along, I'm moving forward, or no, I need to stop and change directions and find a different way to solve it. This is one of the easiest things one can differentiate between novices in a field and an expert, is that novices will tend to pursue an incorrect or flawed approach much, much farther before they realize they need to change direction. So, and there's other aspects of this monitoring thinking, like being able to check if a result makes sense or conclusion makes sense, et cetera, and having quite specific criteria that are used. Now, the research not only identifies these things as it applies to all these areas, but it also makes it very clear that these are fundamentally new ways of thinking for everyone. Nobody is born with these capabilities, and in fact, they only are developed in every area people have studied. They're only developed after many hours of very intense practice that develop these capabilities. And in fact, to reach a sort of, Imperial College faculty level of expertise, it's actually many thousands of hours. And it takes basically everyone pretty much the same time. And I think it's really becoming clear in recent years that this is a basic biological requirement, actually, because we're seeing that that in fact what's happened in these many thousands of hours of intense practice, the brain is actually being substantially rewired. It's growing new neurons, they're connected up in new ways, and it's really within this rewired brain that the expertise lies. And to get the brain rewired that way, it's really very similar to what's necessary if you want to build up a muscle. You got to use the muscle, intensely and over a long period of time, and in response, the body says, okay, he's going to keep using that muscle, I got to make it bigger and stronger. It does very much the same in the brain, and so that's why this intense practice over a long period of time is so essential. But of course, that gives you a very different perspective on learning as well. If you think about, you've really got to be exercising the brain in the right way to learn, not filling it up with information. So I said it takes all these hours of intense practice. What the research also shows is that practice has to be a very specific sort. It's got to be difficult and so on, take a full attention and focus, but it also has to be practicing just the kind of expert thinking that you want. And so it really has to be looking at the particular thinking skills to be developed, and then also there's got to be a feedback process. It's not enough to just practice something. You have to get feedback both on how well you're doing and how you can improve. And so this development of expertise they've seen really involves this very explicit practice of skills and getting feedback to improve, and going this cycle over and over and over as one gets greater and higher level expertise. Now, that's all kind of very generic. I want to give you a little bit of a better perspective of what some of these skills are, specifically in science and engineering, for example. And I could give you a list of about a dozen. I'll just pick a few here. First, something that's true in every area of science and engineering, there's a set of conceptual model or mental models that experts in that discipline use. And most importantly, there's very specific criteria they use for deciding which models are applicable and which aren't in particular cases. Another is every area has particular criteria for deciding if an answer or a conclusion is correct or makes sense or might be improved. And another one is every area has particular specialized representations of information. And so and experts move very fluently between these different representations and get new insights from doing that in order to solve problems. And so these are the kind of things that the learner really has to be practicing doing and thinking and using as they're going to develop expertise. Now, I think it's pretty obvious to all of you that there isn't anything here about content and pieces of knowledge, but in every discussion I've ever had in a department about, okay, what you want the students to learn, it's all about content. It's, do we cover this topic before that topic, and which of these are in different courses, and so on. But the really key thing to recognize here, what the research tells us, is that knowledge per se is not very useful. We get lots and lots of research studies where we'll show that students can know a whole variety of different things, but they don't know when and how to use that information. And so knowledge really only becomes important when it's embedded in these more general aspects of expert thinking that guide the use of knowledge in effective ways. So that's what has to happen in the learner to become more expert, to think in a more expert fashion. So, what's the role of the teacher in this? Well, the teacher has to be, an effective teacher is one who breaks down the expert thinking in a subject and identifies the specific tasks that are at the right level for the learner to be able to practice them, and then gives the feedback to guide the learner to improve. And finally, and this part often gets neglected, they're also, if they're going to be effective, they've got to motivate the learner to realize why it's worthwhile to put in the necessarily intense, serious effort of learning to really make progress. And so if you actually think about it, this is exactly all the things that a good athletic coach always does. And so I sort of think, well, a good way to think about an effective teacher is they're really the cognitive equivalent of what any good athletic coach sort of automatically does. I'll just make a little side note here also, though, is if you think about what's involved in being able to do these things, you realize that it means a good teacher necessarily has to have a very deep mastery of the content. If they're going to be doing these things, they have to know what expert thinking is in a subject, and they've got to be able to evaluate the learners to see whether they're thinking like an expert or not. And so I would say this really is the ultimate justification for the research university like Imperial, where you want to have the people who are the most experts in the subjects are also actually teaching the subjects. Because you simply can't be an effective teacher if you don't have deep content mastery. Now, on the other hand, that's necessary, but it's not sufficient. And so, the rest of my talk is, okay, what do you have to be as you master you great mastery of the content, what do you also have to do to master expertise in teaching to be able to transfer that expertise most effectively? So how do you apply this idea in the classroom of having the students practice thinking like experts and getting feedback on it? And this can be done in different ways, in different settings. I'll give you the example that is most people find the most difficult, which is basically teaching in a classroom that looks like this lecture theater of a few hundred students at once. And I'll use an example from introductory physics. Very similar things I could give you have been done in chemistry and biology, computer science with similar sorts of results, but I'm a lot more comfortable telling you about physics, okay? So let me take the example of if I was teaching introductory class on, electricity. The first thing I'd have the students do is they'd have a relatively short, quite targeted pre-class reading assignment that basically on electric current. And I don't really expect them to get a serious understanding of the physics from this, but I do see this as a much more efficient, cost-effective way to get a basic transfer of information, basic facts and terminology. I can have them read it. I don't have to waste valuable class time with doing that. So they have to read this. I give them a brief online quiz they have to fill out just to check that they've done it, reward them for it. And then they've already got information. I can start class right away with a question. And so, for example, I would take this, this circuit here with light bulbs and battery and ask them what happens to the brightness of that bulb when I close the switch. And every student in class would have a clicker, which is a little personal response system. Hopefully most of you are familiar with them. And students would look at this, they would decide what the answer was, they push the right button, and my computer records, who they were and what answer they chose. Now, I want to say a little bit more about clickers because, frankly, at Stanford, I see a lot of really poor use of clickers in a classroom, and so I want to tell you what they do and don't do for learning, okay? So on the one hand, they give me, the instructor, a very quick idea of whether everybody already knows something or nobody knows it, so that's some quick snapshot of what's happening, the knowledge state of students. But what's more important is what they're doing for the students, actually, because I'm giving them a question in which they have to commit to an answer in which they have some level of accountability for. Usually in many questions I won't even grade them, but they know I can look in there, see what they answered, and see who they were and what they answered. And so that in itself makes anybody, it's basic psychology, think much more intently about the idea, the question, than they would if I just threw it out to everybody to think about. There wasn't any sort of commitment or accountability required. And it's that kind of deeper, more intense thinking actually then really primes them to learn much more from the following activities. And so the first part of that would be, okay, they've all answered individually, and then I don't show them the results, I don't show them what the vote is, but I tell them everybody has to talk to their neighbors, in a big room like this, to decide to try and come up with what the right answer is and the reasons behind it, and then re-vote. And while they're doing those discussions, I'm not standing up here watching them. I'm actually running up and down the aisles or strolling up and down the aisles, listening in on those conversations. So I'm getting little snapshots of what's going on in those students' brains. Where are they thinking like physicists, like I want, and where are they heading off in confused directions that need to be corrected? So after that revote, then I demonstrate the results and show them what the vote was, and then lead a follow-up summary where I go over what's correct, but more importantly, I go over what's incorrect and why. And this is something I learned from my cognitive psychologist friends, which is that you don't actually learn very much when doing something and finding out if you're right or wrong. Where you really learn is when you've done something wrong and you find out why it's wrong, and so how you can change and improve it going forward. And so this is a place where I see many instructors making the mistake of, students all vote, most of them get it right, or some fraction get it right, some fraction get it wrong, and so they'll go over what the right answer is and explain it, and then move on. And it's a big mistake, because you really have to have people understand why they're wrong is where they really learn. Okay, so in this is basically the process. And so if you go back to my original idea or point of how are they thinking like physicists in this process? Well, they're getting practice thinking about, because they're having to formulate a conceptual model for electric current, and they're having to apply it in this situation and test their ideas against what happens, and also test their ideas in their discussions with their fellow students and critiquing their fellow students' arguments. And so these are all very much exactly, thinking scientifically. And while they're doing that, they're getting multiple forms of guiding feedback. They're getting it from talking with other students and getting those ideas fed back. They're getting it from making predictions and comparing that with what actually happens. And probably most importantly, they're getting it from me now, the highly informed instructor, as to what the different thinking is involved in, of going and giving them feedback then on the right and wrong ways of thinking about it. So that's the kind of idea of how you implement such things. And you can do this in different levels and different subjects in just applying much the same principles. And so there have been lots and lots of studies where people take this kind of teaching in various forms, but the same basic principles, and comparing it with the traditional lecture instruction, where you've got somebody up there talking and students are taking notes on it. And a few years ago, I counted up and got over 1,000 studies on this. It's now even more. But in these comparisons, what one sees is that this scientific teaching, call it, it consistently shows greater learning. It shows lower failure rates, and it always benefits all students, but it seems to usually benefit the sort of most at-risk students somewhat greater than the others. And I'll say the one thing that we've been looking at just recently, there's not nearly as many studies on this. We just a few things my own group and a couple others been looking at quite recently, is we see that it actually is increasing, that these teaching methods seem to be much more effective at increasing sort of a broader, more diverse cohort of students. That students that in cohorts that are relatively unsuccessful in certain areas, we see that when taught this way, we bring those students up a larger amount. Okay, so I'm going to give you a few or several examples actually showing these kind of studies and what's been seen. This one I like because it involves many different instructors across many different sections in comparing teaching in two different ways. And the measure in this is taking the basic concepts of force and motion that's covered in every first semester physics course, every university, and seeing how well the students can use these concepts to apply in some simple real-world situation, use them to make correct predictions like a physicist, okay? And we've got some tests we developed particularly target this. And so at Cal Poly, where they did this, they collected data on these many different instructors in many sections, and over a number of years, and they basically averaged here a learning gain of about 0.3, which means the students learned about a third of what they didn't know at the beginning of the term. And that turns out to be pretty standard for a well-taught traditional lecture course. So then they changed to use the approach ideas like I talked about. In this case, they're smaller sections, and so the students are working at tables, working in small groups, and the instructor is going around acting as a coach or facilitator as the students work through a carefully prepared set of problems that they work through. And then so this was in subsequent years, they then tested the students in the same way, and they found that the average learning here had just doubled compared to the traditional lecture setting. And so the thing I want to stress here is that you have the same set of instructors, and there's quite a number of them, but across the board you see large improvements in learning. And in fact, in this, this one I single out because for this particular instructor, they just changed the teaching methods they're using, and those students are learning about a factor of 6 more. So it's really quite dramatic that it's not the instructor, it's the method the instructor is using. Here's from a very different subject, computer science, and using a different measure, the drop and failure rates. And this is work that Beth Simon did at University of California at San Diego. And she came and worked with me for a year, learned this method of teaching exactly like I illustrated with the electricity example, went back to UCSD, worked with the other 3 instructors who taught the sort of core introductory computer science courses there, and they looked at how many students were actually failing those courses. And you can see across all of them, there was a big decrease in the failure rate. And so now what they have is about 1/3 the failure rate that they used to have. Again, same instructors, just adopting better teaching methods. So those studies, and actually most of the work in this field, has really focused on the learning takes place over an entire semester or quarter. And that's the sensible thing to be looking at. That's what you care about. But we wanted to do a research study that, just from a research question, looked at just the learning that takes place in the classroom itself. And so this is the study that I started out with, where we found these 2 sections, a big introductory physics class where the student populations were very much the same. And so one of these courses was taught by someone who, as I said, very experienced, high student ratings, and the other one taught by someone who was trained, new PhD, but trained in my program of scientific teaching. And these 2 instructors, before starting this, they agreed on exactly the material set of learning objectives to be covered, and exactly the amount of class time, 1 week of lecture time to be covered in this. And then both sections were given a surprise quiz right at the start of the next class to see how much they'd actually learned. And the timing was carefully arranged so the students weren't doing any homework or studying exams during this period. So it was just trying to look at what they were taking away from the classroom. We also did this because we wanted to address a question that always comes up with these methods. If people think, oh, gee, you can't cover nearly as much material when you teach this way. So this was a case where we were doing a direct comparison of the same material within the same amount of time and what you could accomplish. And so, and the experimental class design had just the same kind of features that I already told about. Students did a little bit of preparation of reading ahead of time, and then during class they were answering questions with clickers, or since this was more mathematical, they oftentimes were also doing worksheets where they'd have to be writing things down, but again, still talking to each other, having the instructor monitor what was going on, and then follow up with guiding feedback after the students had worked on the problems. And so that's what produced the histogram that I showed you before. Now, the difference between these 2 classes is actually probably is bigger than you probably realized when you first looked at that. And that's because to keep it objective, this was a fairly carefully developed multiple choice test. And so on average, just by guessing, students would get 3 if they guessed at random. So you really have to think of the learning here as how far above 3 are the students. And when you use that standard, you realize just how profound a difference there is between these two classes and how little learning is happening in the traditional lecture class. We also monitored a few other things in this study. We have ways of monitoring student engagement, and no surprise, in the active learning class, the students were much more engaged because they were busy having to answer questions, work out answers, argue with each other as to what was right, etc. The one that really surprised me, actually, but you'll see later on is consistent with other things, is attendance actually increased as well in that class. Okay, I was going to give a biology example, but I'm running a little behind, so I'm going to just jump through this saying, okay, we find out things in biology too. In this case, the quick answer is we showed that the amount of jargon introduced in a typical biology class really inhibits learning, and if you can present the concepts to the students before you fill their brain up, use up all their brain with trying to keep track of all this jargon, they actually learn a lot better. So, but I'll skip that. Okay, so I do want to say something more, though, about more advanced courses, because most of the research has been looking at introductory courses in science because that's where most of the students are and just more easier to study. But in recent years, my group in particular, but a few others, have started to systematically adopt these ideas into more advanced classes. And so I want to just mention that in particular. We've done a little bit at UBC, and Stanford in the physics department has actually done a lot of this. And these are some pictures of what's happening in these courses. Again, students are working at small tables, they're working together on usually worksheets and calculations, and the instructors are circulating around, guiding them, giving them feedback. And I should say, for those of you interested, we wrote up a paper that was really quite detailed and careful way of laying out exactly the design and implementation of such a course. And it doesn't, okay, this was modern advanced optics, but that's kind of irrelevant. 90% of the paper is about, you could apply to any more advanced science or engineering course. So, okay, we wanted to measure how well it worked, and so this is one of the measures of learning where we had some particular challenging and authentic questions we could put on every year on the exam in some similar forms, and basically when the course was converted to this active learning mode, those improved by about a standard deviation gained on the students. At Stanford, just over the past year and a half, dramatic increase across. They're extremely positive, actually, sort of overwhelmingly, and now the students are sort of pushing the faculty to change other courses because they find it's just so much more valuable to them for their learning. And finally, well, there's actually two features here, points here. I do want to say I need more years of data to be sure this isn't just a statistical fluke, but we've seen just in the past year, when with all these courses changed, the number of physics people saying they're going to declare and stay as physics majors has gone up dramatically, and the number of women who are going into physics has just about doubled. So those are very striking numbers. As I say, it's only 1 year. We got to make sure they stay that way. Okay, but finally, I want to point out that the effect on the faculty, that all the faculty have found this is much more rewarding way to teach, and they all want to teach. keep teaching this way because it's just a lot more enjoyable than lecturing to the students. And I want to sort of emphasize that this is actually a typical response that we've seen. At the introduction was mentioned, I launched these big initiatives at British Columbia and Colorado where we have something like 200 faculty and something over 200 courses have been transformed this way. And we see this as quite a consistent response from the faculty, that they all just enjoy teaching this way much more. And so although it does take some time to learn, once they've done it, nobody goes back. So that takes me to the last couple minutes of my talk, switching into talking about institutional change. If you've got something that you've got data showing it's much better for student learning, and the faculty like it once they've invested the time, ask, how come everybody isn't already doing it? It seems to make a lot of sense. And so I'm not going to tell you the details there, but I will. You can go read my book on this. But basically, this was what the science education initiatives were, is really a large-scale experiment to try and implement these things widely and see what factors were important in this. And so, we did succeed in changing a very large number of courses, and, most of the student credit hours in science now actually are taught by different, more effective methods here. And some of the key components are likely to be being copied, or I don't want to prejudge things, but some of the things we found that were really effective in this were competitive grants to proposals, where much of the and these were substantial grants, where a big fraction of that went into actually hiring and making sure they were trained these science education specialists within a department. So departments would hire people who were experts in the subject, but then also were experts in teaching it, and then they would serve as a departmental resource working with the faculty to implement these methods. And that seemed to work very well. They provide labor and expertise, which are two key things in changing to this kind of teaching methods. Now, I will tell you that we've also sort of looked at how much time it takes a faculty member to go from, being an expert in physics or biology or computer science to also being a pretty expert teacher in these subjects using this research-based methods. And of course it varies, but with some reasonable level of support, it's about 50 hours. Now, that's not an overwhelming amount of time, but probably most of you don't, look at next week and think, gee, how am I going to use all those 50 extra hours that I have spare time, right? So, it's a non-trivial issue here. And the big barrier we found against it, and I think it's true everywhere, is really the formal university incentive system. And the problem is that, the universities I worked with, and essentially every one I've ever heard of, which is a lot, they just have very flawed ways of evaluating teaching. They're basically student evaluations. There's lots of data showing how flawed those are, and particularly they don't really capture the effectiveness of the teaching methods that are being used, because students usually aren't in a position to be able to make those comparative analyses. And so the result is, if you've got a very flawed evaluation of teaching, it's not given much weight appropriately, and everything is weighted on research. And so basically, the reality is, with the current incentive system, if you go off and spend those 50 hours to become a better teacher, the incentive system will punish you for it, compared to if you'd written another paper. So that's really the fundamental problem that universities have to get over here. And I'll say we've worked hard on a better way to evaluate teaching, and I won't take time to go into it here. You can go read this paper. But basically, it's a way of evaluating the extent of use in teaching a course of research-based methods that research shows are more effective at supporting student learning. And I think, so ultimately, universities are going to have to move towards that direction in much the same way that, hospitals, when they realize that if doctors wash their hands, patients don't die, they, after 50 years or so, they realized, okay, because of that research, they get around to actually monitoring whether doctors were washing their hands, and because that's what you need to actually have people do it. Okay, so let me just finish, so there's time for questions here. The first point I want to summarize is that really stressing that a meaningful education in science is really about learning to make decisions and choices better within the relevant areas. And the research is really giving us new insights on how to do this better for all students and how to be more effective at teaching. And this scientific approach, the data we're getting more and more is that it improves student learning, it doesn't hurt student happiness, often improves it, and that the faculty really find it a more rewarding activity as well. And so I'll just mention, I'll make my slides available so that you don't need to remember all these things. But if you want to learn more, these two books are sort of my two favorite references. And one of the things is, here I talked a lot about general principles, but there's a lot of details you have to get right of implementation, just like if you want to do a physics experiment, there's a lot of little complex details involved in expertise, which you can't avoid. And we've tried to capture a lot of those things on the resources page of the CWSEI, so you can go look. If you want to do any particular thing in a class, you likely can find a 1 or 2 page guide on details of getting that right. And so I'll mention that website. So with that, thank you for your attention.
So for those of you who don't have to leave yet, who would like to ask a question? There are people around with microphones. There's an abundance of people over there, so you can actually stay there. Why don't you start at the top and work your way to the bottom? Would you introduce yourself? Tell us who you are before you ask the question.
So I'm going to interrupt since I've done this a lot more than Simone probably.
Okay, go ahead.
And the business of having people raise their hand and run around to take microphones is really awkward. So let me suggest if you have questions, you might actually just come to the aisle and they can hand the microphone back there instead of trying to get them moved through the room.
Great.
Okay.
Come to the aisle then. Let's
or the future people, just so you can get a microphone easier.
I'm Thomas Clark, Electrical Engineering Department, and I teach mostly computer science. And I guess I've been doing something a bit like some of this stuff for 2 years now. So I have one question for you relating to the dramatically better meeting of learning objectives, which is what I found as well. How much more time do the students taught in the scientific way take doing their out-of-class reading than the ones taught in the normal way?
Yeah. So in the courses where, so that one I don't know. I mean, the one course done at Cal Poly, I don't know. In all the courses that we were involved in and that I have data on, we actually made the time stay the same. Okay, so what that meant was the amount of time they had to spend in preparation for class. You had to think carefully about what was an optimum there. We try to keep it no more than half an hour, and we then reduce the homework that they do after class by a corresponding amount to keep the level of student time invested the same, because I'd argue, sure, if you just insist students spend infinite amounts of time, they'll learn more, but that's not really fair. They have, you've got to balance the demands. I will say, and this is an important point, is we push hard in the courses that I work on that people transform to monitor much more carefully than is usually done the amount of time students are actually spending, so that one can set reasonable expectations up front and then adjust the workload to make sure that those are appropriate, because oftentimes the students are spending either much less, usually much less, sometimes much more time than the faculty really recognize. And so that's an important data to know about, I'd say, when you're teaching. Okay.
It's Imperial, it's often much more.
Yeah, but in these cases, for the research, we keep the timing controlled for that.
Why don't you walk down with the microphone then?
Yeah.
Maybe.
Anyway, okay, yes.
Hello, can you hear me? Can you hear me?
No, is the microphone working? It's hard to hear up front.
Is there just one microphone?
Could you try again?
Just talk loud.
Okay.
I'll repeat it.
That's not going to work very well, but I'll try. I'm Geoffrey Vernon from the Department of Medicine. I've taught both physics and medicine, or physics and biology, and the difference between the two subjects is that physics is much more theory-rich. Biology and medicine is just full of facts and factoids. And when you talk to your colleagues in medicine and biology, they say, I have to teach my students all this stuff. There are 35 chapters in my textbook, and the students have got to learn all of that. How do you think we can overcome this view that somehow the textbook provides us with the syllabus? And that's what the students should be learning rather than paradigm cases.
Yeah. So, I mean, if it makes you feel any better, I can give you a number of physics textbooks that are 4 or 5 times too long for what you can possibly cover. So it's not just physics. It's, so this is a challenge across all fields of, okay, what do we really need to cover and how much should it be? And textbooks are the worst, are really a serious problem in this area, and it really comes from the fact that textbooks are written not to teach students. Textbooks are written to sell, or published to sell textbooks, okay? So in the process of writing a textbook, what you do is the instructor might teach a course, they write it all down, the publisher sends it out to 50 reviewers and gets back 49 comments saying, well, this is pretty good, but they left out this topic that I really like, and so then they add 49 additional topics. When the instructor who wrote the textbook, they never cover all the stuff in their textbook because a whole bunch of it's gotten added. And so, this really gets to the point that in thinking about a course, instructors really need to focus on what are the real objectives? What do I really care about students knowing, learning, and usually being able to do maybe a year or 2 years later, and I'm going to really focus on those, and I'm not going to cover everything in the textbook, and I'm not even probably going to cover everything that was taught in this course previously. But you're absolutely right. You can't, if you're following a textbook, you're making a terrible mistake, and because that's just not what they're designed to do. Yeah, go ahead. Go ahead, and I'll.
Right. A very interesting new way of teaching. Did you find that you also need to introduce a new way of assessment?
So his question is a new way of teaching, do we also address a new way of assessment? And the answer is yes. And you get different results depending on what you measure, okay? Now, all the things I show you of getting the most dramatic results are really things that are focusing on very much thinking like a scientist in that area and making these decisions. If you test students on have they memorized a bunch of facts, have they memorized calculational procedures, you won't see very much difference. And in fact, because those are things students learn by practicing outside of class doing homework anyway. And so that goes back to the previous question, really, is that as part of the transformation, we work on people thinking hard about what they care about students really learning, making sure their assessments are aligned with those learning goals, and then also making the teaching also support those. But you really have to have all of those things aligned together, okay? Yeah.
Too many questions. I'll let you.
All right, sorry.
I'll let you
Is there a
take several.
microphone that's working somewhere or not? Okay, go ahead.
You speak right into it?
Okay, you're next, sorry.
Right. I'm Vijayaratnam. Actually, I was in Colorado for a conference in 1981. I wonder whether Professor Ilagna Segura, your colleague in Colorado University, he's the head of Department of Civil Engineering, my batchmate. I was recently appointed by the President Obama to the science policy in underwater mathematical modeling. Are you aware of it now? Never mind. What I'm trying to say is, the traditional way of teaching, he was my batchmate at the first year, and nearly half of them failed. All the brilliant minds. What really happened was, all the PhDs, probably some of them from Imperial College, and they behaved like the ivory tower. And
Sorry, is
and
there a
half
question
of the,
here? What's the question I'm missing?
what I'm trying to say is, although they teach us, and they parallel there are experiments every subject they teach. So in engineering, the teachers teach, and the laboratories we have experiments all the time. Every week we have their assessment after that. So in engineering, I don't know about physics, but engineering, parallel there are experiments going on to test the theory they teach. So I don't know where your new style of teaching is different from original way of teaching, traditional way of teaching.
I think I'll just pass on that question. Can you, I can't answer.
Hi, Phil Ramsden. I'm a teaching fellow from the mathematics department.
Yeah.
One of my interests is online learning.
Yeah.
In a lot of ways, a lot of online learning environments resemble the traditional lecture.
Yeah.
The student sits in front of their computer or their tablet and views the content. What in your view marks out those online environments that embody your principles or the principles that you've been?
So, I mean, clearly online you can pose questions to the students, have them think about answering. You can get some forms of feedback as an instructor on how well they're doing and give targeted feedback to them. So those things, I think, you can sort of see how an appropriate online would capture. One of the aspects that I see the most difficult to capture with online learning, and I think it's just a technical or technological limitation, and it's a it will be solved, but I struggle with how to do it right now, is the fact that I can have students in the classroom talking to each other, and that level of communication where if it's online, the talking, they're making sketches, they're hand gestures, etc. And so they're able to communicate more readily than you can do online. And as an instructor, I can listen in on those or watch what they're doing. And so that's the part that I think is the most problematic, or where one needs to think the hardest about capturing with online. But otherwise, having students prepare ahead of time, working on tasks, sharing their answers, and then getting some feedback from the instructor after the students have been prepared to learn from it. Those aspects, I think, you can expect to accomplish online.
Thank you.
Okay. I should get to this side of the room next. A little biased here, sorry.
My name is James Williams. I'm actually not from Imperial, I'm from the University of Sussex.
Okay.
And I'm a lecturer in science education. What you've described tonight is the way that science educators in the education departments have been teaching, well, certainly I've been teaching that way for the past 20-odd years very successfully.
Yeah.
When you ask other faculty to do the same, and you give them the chance to change or prove that there's no need to change, most of them get busy on the proof rather than the change. One thing that you put your finger on right at the beginning was a difference between knowing and understanding. You said that they came to you, those physics graduates, knowing a lot of physics. They passed a lot of tests.
Yeah.
What they understood of physics was very, very little. And I think there's a fundamental flaw in the way we teach science, in that we do not teach about the nature of science. We do not teach, certainly children in schools and undergraduates, about different ways of thinking, inductive thinking, deductive thinking, abductive thinking. And I think that the language of science is completely muddled, in that if I asked everybody in here who are, I would think, mostly scientists, to give me a definition of a theory, a law, a hypothesis, and a principle, I suspect we get many, many different definitions, and not all will agree. So how do we solve that problem of the language of science, the methods and the methodologies of science being quite different from physics to biology, as was illustrated by an earlier question, and at the same time overcome this problem that the transmission of knowledge is thought to be the best way of teaching?
So, I mean, so first I'll take slight issue with you on the difference between physics and biology. I think if you actually look at how experts, if you step back from how the knowledge is laid out in textbooks and you actually look at how experts work in the subject, they're much closer than you'd say. But that's a side issue. I think in terms of convincing people to think about this differently, I mean, I'm hoping that this kind of research will convince people. And I will say the research supporting these methods is really much stronger at the university level. And I'm not saying that anything you said was wrong or that it doesn't apply at the school level. It's just because you can do so much more controlled studies, you can get much more dramatic results. And so, that's why I go around hoping that I talk to people about the research and the ideas, that will convince more and more people to start teaching this way. Universities, like Imperial, will be able to then show that they're using more effective methods. They'll get more students, they'll get more funding, and then that'll change the system. But it's a big, complicated system, as you well know, so it's a slow process. Somebody over here? No? Yes.
Judith Hackett, I'm not from the university at all. Well, I am. I'm a graduate of the university, but a long, long time ago. Here in the UK, one of the challenges that we have is getting people to be scientists and engineers in the first place. They're turned off by the way it's taught in schools.
Yeah.
How much do you think this methodology is applicable to the way science is taught in schools?
So the question is, how much is applicable to the way this is taught in schools? So I'm going to answer that question for North America, particularly United States, and not prejudge what happens in UK. So the quick answer is the ideas are much the same. They obviously, as you go to lower grade levels, you shift in terms of what the goals are, but the ways of learning are quite applicable. In terms of getting more students to go into it, though, what I always point to is that we lose a lot of them at the university level, and these methods, can make a big difference there. But more importantly is that these methods, as I said, they really require a deep understanding of the subject. And in the United States, with some notable exceptions, the teachers at the school levels just don't know the subjects well enough to apply these methods. And, so who's responsible for the fact they're graduating from university without knowing the subject? That's all of us. And so I look at it as ultimately you could have a much bigger impact if you applied it at all levels, but it's clearly the first necessary step, and that is at the university level. So we can't really point our fingers and say, go fix it down there. So, yeah. Okay, there's a microphone.
Time for 2 questions.
Yeah, okay. And we have a microphone for him.
Hi, I'm Jordan Nash. I'm the head of the physics department here. You showed something really interesting, which was with a really well-designed course, you could get a PhD, just fresh minted PhD, to get much better results.
He wasn't fresh minted, but 4 years out. But anyway. Yeah, that's right.
I can see there's a huge win to having the experts designing the material.
Yeah.
Where do we leverage the experts for the delivery of the material? How do we get the extra value added because we're Imperial doing this as opposed to someplace else using Imperial's material to do this?
So this is, I'm really glad you asked that question, because with teaching these ways, you can't give these materials to somebody and have them be a good teacher, because an enormously important part of this teaching is that ongoing feedback and monitoring of the students and what they're confused, and each new crop of students has a different set of questions. The students in general, you'll find when you teach this way, there are many more questions from students than you get in a normal lecture, and they're much deeper questions. And so it's much more demanding of the subject expertise, and they're different every year. And so you have to, you can take a good set of materials, but you need people with the kind of deep expertise in the subject in the room there, ongoing basis, to support the learning, because it just won't work otherwise. You tell which one to take.
She has a mic.
Okay, fine, okay.
I'm Crystal Foblets. I'm Director of Undergraduate Studies in Electrical Engineering. So can we go back to the time that needs to be invested in changing?
Yes.
So
yeah.
You have highlighted that it takes about 50 hours to learn how
Yeah.
to change.
Yeah.
So can you give us an estimation how much time it would require to actually change your lecture? Yes, you have to prepare something for the students to do before they come, then you have to prepare your questions, and preparing questions takes an awfully lot of time. Yes.
Yeah. So that was in those 50 hours, really, that when we look at faculty from UBC, for example, who and I gave you the example where they had a course which they had lectured on, and now they were transforming it to teaching this way, developing all the different materials and activities. They found it was about 50 extra hours, okay? So it's actually, if you're going to teach a course for the first time, you don't have anything to rely on, it's actually not that much more, because that kind of time people invest. I'm saying under normal circumstances where people already have notes and materials, they found that it took them about 50 hours. But that was the whole package. Then in subsequent years, you don't need that extra time. It takes about the same amount of time as the regular lecture methods.
Maybe the very last question for the gentleman all the way in the back.
Okay.
Then I think we really need to stop.
Okay. Okay, somebody needs to give him a microphone, or you need to yell louder, sorry. Yeah, okay.
There's a mic coming.
Okay.
Okay, can you hear me?
Yeah.
That much better? Right. I'm Wayne Mitchell from the Department of Medicine. I'm a teaching fellow. One of the things which you mentioned was about the mastery mastery of content versus the mastery of teaching.
Yeah.
How do you get a balance between the demands of the mastery of content, which Imperial, which is really good at, with the mastery of teaching? I'm not sure how good we are at that. How did you get that balance where you were?
So I'm not going to talk about the balance where I am, but I will talk about, the 200, or now if I start adding in Stanford, 250 case studies of what it takes people who have mastered the content to become, good, effective teachers using this method. And that's what I was saying, that's sort of an extra 50 hours. Now, if you want to look at what it takes to master a content in biology or physics or any subject you want, it's more like 10,000 hours. And so what I'm saying is that, and this is kind of the standard I'm happy with now, is we can take people who put in all of that time to master content, and within a few tens of hours, bring them up to a much higher level of teaching expertise than they were before. And so that's where I think realistically is kind of the sensible approach to go right now, because we have the content, we have the content experts already here. We can just make them much more effective teachers in really a very relatively small amount of time invested.
Thank you. That was great. And now Professor James Sterling wants to say a few words.
Okay. Once again, I find myself unique thing standing between you and the refreshments. So I will be brief. It's common on occasions like this for people like me to say thank you for the inspirational lecture. Those words somehow don't do justice to what we've just heard. This has been truly inspiring, informing, inspirational, illuminating, entertaining as well. So Carl, thank you so much for what you've just done for us. And it's great to see the lecture theatre so full. There is an enormous amount of interest in this across college, and we will take away so much from your talk tonight. Thank you also for agreeing to spend tomorrow with us. We're making good use of Carl tomorrow. He will be around college having meetings with various interested groups. Simone mentioned that this is so timely because we are in the process of launching our new learning and teaching strategy. Many of the concepts that Carl talked about this evening are embodied in that strategy. Now, that isn't just a happy fluke or a fluctuation or anything. That's because you've already inspired. You've already inspired through your published work and your conversations with Simone and others at Imperial, the way in which we've constructed our new way of doing learning and teaching here. So thank you for that inspiration through your published work, and again for your contribution tonight. And if I could just end on a personal note, because I was reflecting as you were speaking on my own personal journey through teaching. I started teaching in 1986, teaching undergraduates, and I had a stick of chalk in my hand and there was a blackboard. I gave my last undergraduate lecture in 2012. Wasn't the same stick of chalk, but it was a stick of chalk in my hand, and the blackboard was still there, and it was probably the same course I was teaching. And over those 24 years, it began to dawn on me at some point, this isn't much fun for me, and looking out, it wasn't much fun for the students either. And I began to think, is there a better way of doing this? But to be honest, I was so frightened. I didn't know there was any other way of doing it, and I was so frightened of doing it differently in case I messed up and destroyed all these young people's lives. So, but you've done the experiment. You've split the cohort. You've done the 250 this way and two that way. You've done that. You've studied it in great detail. You've done the scientific experiment. You have the data. We have the evidence. We don't need to do that. We can just follow the principles and the methodologies that you have and others have discovered. So thank you for that. The last thing I want to do is to give you a small token of our appreciation. So thank you very much. Thank you. Fantastic. Thanks very much.